Hello, this clip looks at summarising phenols in terms of their reactivity and why they're a little bit more reactive than normal benzene-based compounds. So what is a phenol? A phenol is basically any aromatic compound that has an OH group attached directly to the benzene ring, like this. So some examples are shown below. So you can see how 2-ethyl phenol is a phenol because it's got this structure here as part of its molecule. So that is a phenol, and the other one, 2-phenyl ethanol, is not a phenol, even though it has phenyl in the name. Okay, so the phenyl just refers to the fact that you have an ethanol molecule with a benzene ring attached to it at some point. So why do we consider phenols separately to other benzene compounds? So first of all, let's have a look at why phenols are more reactive than other aromatic ring type compounds. To do this, we have to go back to the original model of the delocalized pi system in benzene. So if we take the delocalized benzene model with the pi orbital overlap, and the perpendicular pi orbitals of the carbon atoms above and below that are overlapping, and we build the equivalent model based on phenol, you'll notice that where the carbon is bonded to the oxygen on the OH group, that lone pair on the oxygen becomes delocalized into the pi ring, so it increases the electron density by 2 extra electrons. So comparing the two, it's clear that phenol has a greater electron density than benzene. If it's got a greater electron density, that means it's more likely to react with electrophiles than benzene is, which has implications for how it behaves. So now that we've established the reason behind phenol's extra reactivity, let's have a quick look at some of the reactions that phenols undergo as opposed to the reactions that benzene and other aromatic compounds may not undergo. So when I say that they don't undergo those reactions, what I'm talking about is the aromatic ring on those aromatic compounds not being involved because of its relative stability. So the main reaction that you look at A level is to compare the bromination of benzene as opposed to the bromination of phenol. So you may or may not have had a look at the bromination of benzene at this point, but let's have a look at the bromination of phenol. If we take a phenol molecule, bearing in mind now that we have extra electron density in the ring, and we simply react it with bromine water, like so. You'll get multitude of brominations, generally at the 2, 4, and 6 positions. Like so. So remembering that because the dominant functional group on phenol is the phenol functional group itself. So let's remind ourselves of that fact. The phenol functional group is this whole thing in its entirety, not just the OH that sits on it, but the whole thing. So going back to our reaction, we obviously have 3 HBr Okay, so whilst we're on the subject of the different reactions of phenols, let's just put a couple of ideas across that clarify their difference between other compounds that might have OH groups in them. We've talked about other compounds that might have benzene rings. It's important to remember that phenols, even though they have ol in the name, they're not alcohols. So let's look at another reaction of phenol. Phenol can behave as a weak acid, so it can partially ionize to form the phenoxide ion and H+. So let's separate the page out slightly so we can consider the two different reactions separately, like so. So if we've got a phenol molecule, like this, what it can do is it can ionize or dissociate into the phenoxide ion, which we talked about in the last slide, and H+. So that now means it can do things like react with bases, or it can react with metals. Okay, so what we've just seen there is the phenoxide ion. So I'm just going to label that so that we can see what we're talking about while we discuss it. For example, if we were to react it with sodium hydroxide, it would do this. You'd have your phenol plus NaOH giving you sodium phenoxide. So the sodium bonds ionically to the phenoxide ion, and the phenoxide ion maintains its delocalization of the pi system, and it has its 8 electrons that are delocalized into the bond, into the pi system, etc., like we talked about before. And similarly, if we reacted the phenol with sodium, like this, you would have, again, sodium phenoxide, but this time you'd have hydrogen, because you're reacting a metal with an acid. Let's tidy that positive sign up a little bit. So to be careful here, you're only losing one hydrogen, so it's half H2. Like that. So the other thing to consider is the relative ease of bromination of phenol, cyclohexene and benzene. That's covered in a separate video.